All right, I think we'll go ahead and get started. So we've got several people joining us now. Welcome to our second seminar of the semester for the Soil, Water, and Climate Seminar Series. My name is Kelly Wells. I'm a research scientist in the department, and I'm a co-organizer of the series along with Pusede Sharma and Kyle Sherbine. This semester, we've invited several speakers to speak on topics related to environmental justice, as well as diversity within our environmental sciences community. And that includes today's speaker. And I wanted to mention that in support of this theme, we received a generous donation from Deborah Allen, who most of you know is an emeritus professor in our department. So I wanted to say a big thank you to Deborah for that. So without further ado, I'm excited to introduce today's speaker, Dr. Sally Pusede. She is an assistant professor in the Department of Environmental Sciences at the University of Virginia. She received her PhD in chemistry from the University of California, Berkeley in 2014, and was a NASA postdoctoral fellow at NASA Langley Research Center. And Dr. Pusede's research group is primarily focused on two issues. First is the controls and consequences of air pollution variability within cities around the world. And second is the interactions between air pollution and Earth's biosphere. And to do this work, she and her students combine lab, field, aircraft, and satellite observations. So I will turn it over to you now, Sally. Thank you for being here.
Well, thank you so much for inviting me. I'm really looking forward to sharing this work with you today. So I'll go ahead and share my screen here. Okay. Just get myself situated. Okay. So so the title of my talk today is Nitrogen Dioxide Air Pollution Inequality, and observing this inequality using high spatial resolution remote sensing. Before I begin, I want to acknowledge the work of a graduate student named Angelique Dematillo, who did the bulk of the work that I'm going to share with you today. And about 60% of this talk was published recently in Environmental Science and Technology. So if you want to check that publication out, you can. I also want to acknowledge my many co-authors and our sources of funding. So in this effort to directly observe nitrogen dioxide air pollution inequality, I want to start here with the portion about nitrogen dioxide. So nitrogen dioxide, or NO2, is a short-lived urban air pollutant. It's a criteria pollutant, so it's regulated by the US EPA. And it comes from high temperature combustion and is emitted by vehicles, power plants, and a few other sources as well. It's a widely used proxy for toxic combustion emissions in health research. So the same sources that emit NO2 also emit an array of different toxic pollutants. It's chemically reactive in the atmosphere, going on to form other pollutants such as ozone and particulate matter. And a key element of this talk is that NO2 is detectable from space. So you're looking here at a map of NO2 measured by NASA's OMI satellite across the United States. And you can see that NO2 is an urban air pollutant. And in fact, we could pick out almost every major city across the United States simply by where NO2 is high. So we can see here Los Angeles, Houston, Chicago, New York City, Atlanta. We can pick out all of these major cities across the United States. But what we can't see, if you look, for example, over Los Angeles here, is how NO2 is distributed within cities, or what the intra-urban variability of NO2 is. So we have evidence that there's substantial intra-urban variability in NO2. And that evidence in part comes from the fact that air pollution is generally worse in neighborhoods where residents are primarily people of color and have lower household incomes. And I'm going to provide you with two definitions here. The first is environmental racism, and this comes from Dr. Robert Bullard. And the definition is that any policy, practice, or directive that differentially affects or disadvantages individuals, groups, or communities based on race or color, whether intended or unintended. I'm also going to provide you with a definition from the US EPA, where environmental justice is inequality or inequity with respect to the development, implementation, and enforcement of environmental laws and policies. So these inequalities in air pollution cause measurable differences in health and life expectancy. And despite improving air quality in cities across the United States, air pollution inequalities persist. And I'm showing you a figure from a really nice paper, which was of work done here at the University of Minnesota by Laura Clark, Dylan Millay, and Jillian Marshall. And what they did was look at the change in NO2 disparities from the year 2000 to the year 2010. So this is for all groups across the country. And you can see in the year 2000, we have large disparities with race, ethnicity. But with these large decreases that came in NO2 from the year 2000 to year 2010, we see that these disparities in NO2 pollution persist. So one of the main challenges that we face in studying environmental justice is an analytical one, and that there are currently limited air pollution measurements that resolve neighborhood scale variability. So on the left here, I'm showing you that same satellite image collected by NASA's OMI satellite, zoomed in now to Los Angeles. And we can see that NO2 air pollution is high within the city, but what we don't see is any variability in that NO2 air pollution. But what we know is we would expect NO2 gradients or distance decay gradients to be as steep as a few hundred meters to a couple of kilometers. On the right-hand side here, you see NO2 as measured by the US EPA monitoring network, and each one of these circles represents a monitor, colored by the concentration of NO2 at that monitor. So Los Angeles is one of the best monitored cities in the world, but still just 5% of census tracts are located within 2 kilometers of a monitor. So we have a combination of data that is coarse resolution or these observations that are sparse. So for most trace species, especially short-lived primary pollutants, spatiotemporal variability within cities cannot be captured using traditional monitoring approaches. So we can infer higher spatial resolution gradients using models and measurement model hybrids. Typically, though, this requires long time averages. So on the left side, you see a spatial interpolation. This is of PM2.5, another pollutant in the atmosphere. But this is also in the Los Angeles basin. And so the coloration here indicates the PM concentration. So we still see, even though we have a spatially comprehensive data set, we still see smooth gradients. And on the right here, we see data from a land use regression model, where here we do see this NO2 pollution is elevated over places where we would expect it, major urban centers, roadways, etc. But in both cases, we have long time averages that lack temporal information, which is useful to us for source identification and for understanding the impacts of transient extreme events. So this talk is going to focus on using high spatial resolution remote sensing observations to look at air pollution inequality. And again, I'm showing you some of these observations over Los Angeles. On the left here, you're looking at data collected in the morning. So we can see that NO2 air pollution is high over Los Angeles. We can also make out Los Angeles International Airport, the Port of Long Beach, many of these major roadways. And then we can see also that there's lots of temporal variability. So the data from the same day, but collected in the afternoon, are shown on the right. And now we start to see these point sources really dominate the map, where the Port of Long Beach, the plume from Los Angeles International Airport being blown downwind. So we can see some variation in the sources and dominance of these sources as a function of time of day. So in this talk, I'm going to do 3 things. I'm going to use novel airborne remote sensing to describe NO2 inequality. I'm going to focus for the first part on Houston, Texas. I'm going to evaluate whether comparable inequalities can be observed from space. And finally, I'm going to analyze NO2 inequality in major US cities using satellite observations. So a little bit about these airborne remote sensing data. So these high resolution data capture sub-kilometer gradients. And the specific instrument that I'm going to discuss today is called the Geostationary Coastal and Air Pollution Events Airborne Simulator, which I'll abbreviate throughout this talk as GCAS. So GCAS makes hyperspectral measurements of backscattered solar radiation in the UV. It has a 2D CCD array detector for 2D NO2 mapping with the long track coverage generated by the host aircraft. And the native spatial resolution is on the order of tens of meters, but some spatial averaging is required for signal to noise. And what we end up with actually is a product that's resolved to 250 by 500 meters. And the retrievals use algorithms similar to major satellite instruments, in particular, the satellite I'm going to talk about later on called TROPOMI, which makes the direct comparison a little bit easier. So now you're looking at GCAS observations across the city of Houston. And so you can see here the flight path as it moves across the city of Houston. And you can see here that it's collecting sort of elevated NO2 around major point sources. This is the Texas City refinery. This is the Houston Ship Channel. And we can indeed see some major roadways reflected in these data. And these data were collected as part of a NASA mission that took place in September 2013 called Discover-AQ. And we have 9 weekdays of data with 4 circuits collected per day for a total of 35 circuits. So this gives you a little bit of a sense of the methodology. So what we do is we take these observations here and we average them to the underlying census tracts shown on the left. And what we see is that GCAS does indeed resolve neighborhood level NO2 when we define neighborhoods as census tracts. And this allows us to directly map NO2 at the census tract to demographics, which we also have at the census tract. So with these data, I'm going to ask 2 questions. How does NO2 abundance vary with residential demographics? And how does census tract level inequality vary temporally? A little bit of background on Houston, Texas. Houston, Texas is well known for its poor air quality, which has been attributed to the petrochemical industry, transportation, and the local land sea breeze. It's a large and diverse US city, and it does indeed have documented air pollution inequality. And this is a picture taken from Houston's Ship Channel. So you can see here's downtown Houston here. So to orient you on this map, this photo was taken about here, looking toward downtown Houston. Okay. So here's an example of the type of temporal variability we observe in GCAS observations. These data were collected on 2 days, September 4th and September 24th, and they were collected in the early morning, 8 a.m. to 10 a.m., in the mid-morning, in the early afternoon, and in the late afternoon. And what we see is that certainly we have in areas of really elevated NO2, but we also see quite a bit of temporal variability in the distribution across the city. So I'm going to go ahead and show you the results here where we calculate the population weighted NO2 column. And we do so here for a set of different groups. We look at NO2 for individuals near the poverty line and below the poverty line compared to above. And what we find is that for near the poverty line, NO2 is 15% higher than above. And for individuals below the poverty line, NO2 is 28% higher than for those who are above the poverty line. For race ethnicity, Hispanics in Houston experience 32% higher NO2 than whites. Black and African Americans experience 19% higher NO2 than whites. And for Asians, NO2 is 11% higher than for whites. And we can combine race, ethnicity, and income into this metric defined here as LIN, which stands for low income and non-white or Hispanic, or HIW, which stands for high income and white, and this does not include Hispanics. And what we find is that for low income and non-whites, the NO2 is 37% higher than for high-income whites. Now what I'm showing you is a figure from each individual flight. So each one of these circles connected by a bar represents a single flight. And what we find is that there's quite a lot of day-to-day or temporal variability in the absolute or relative value of inequality, but that inequality was always present. Another observation that we have is that NO2 columns were at least twice as variable for low-income and non-whites in the city of Houston than for high-income whites. And if we compare this to the inventory, what we see reflected in the data is that we actually have more sources and more NOx emission source density in these neighborhoods. And in the case of Houston specifically, we have 5 times more dense NOx sources for low-income, non-white, and Hispanics than for high-income whites. So on the left here, I'm showing you, this is the same figure we just saw. And on the right, I'm showing you that same data, but I've added in an extra day that I had actually removed. And these data came from an extreme air quality event that took place during Discovery Q. So you'll note the difference in Y scales here. So here we're going from 4 to 14, and now we're going from 5 to 40. And during this extreme air pollution event, we saw inequalities by race, ethnicity, and income as high as 84%. And so just as an observation, when we saw the highest NO2 inequality was also when we saw the worst ozone air pollution. So ozone is considered a regional air pollutant. We actually don't see steep intra-urban gradients in ozone because it's a secondary pollutant. It has a relatively long lifetime. But what we do notice here, just from those Discovery Q flights, on days when ozone is high, as defined as an exceedance of the US EPA standard, we find that this percent difference between NO2 for low-income non-whites and high-income whites was substantially higher on days when there's an ozone exceedance than when there's not. And so from this, we see that conditions that lead to high NO2 inequality correspond to elevated regional ozone pollution. And so this suggests to us that reduction in inequality will actually have regional air quality co-benefits. And we'll return to this in a second, but I think from a regulatory perspective, this connection, which could be really powerful. Okay, so to summarize here, using these GCAS observations, based on the average of 35 repeated flight circuits, we found 37% higher NO2 for low-income non-whites compared to high-income whites. And we also saw substantial inequalities when separated by race, ethnicity, and poverty status separately. We saw that population-weighted NO2 was always higher for low-income and non-white residents, despite substantial temporal variability, and that NO2 inequality was severe during a regional ozone air pollution event. So in the next part of this talk, I'm going to address this question of, are we able to measure NO2 inequality using recently launched satellite data? Specifically, the name of this satellite is TROPOMI, and it was launched in 2017, and it produces near daily NO2 maps at 3.5 by 5.5 kilometers, and it samples every day at about 1:30 p.m. locally. And TROPOMI's spatial resolution is about 10 times finer than OMI. And you'll recall OMI is the data I showed you very early on in the talk, okay? So one of the reasons why we would be motivated to do this is the GCAS data do indeed capture these steep gradients within a city, but we don't have a lot of them in a lot of cities. Because it's part of a large-scale aircraft campaign, we're limited by the number of GCAS data we have. But we have TROPOMI data everywhere, almost every day. So here you're looking at the city of Houston as seen by the TROPOMI sensor. And again, you can see downtown Houston. We can see this elevated NO2 over the Houston Ship Channel. We can also make out the Texas City refinery and a large power plant called the W.A. Parish Power Plant. And we're going to ask here this question: what is the potential for satellite NO2 data to describe, explain, and inform policy on inequality? So the first step is to just compare these to the GCAS data. We're treating the GCAS data as a standard, a calibration standard. So we take the TROPOMI data and average them to the census tract, and we also average them along the GCAS flight path. And for a variety of different dates, we can see here for September 2018, annually, and just within the urbanized area, which is this black boundary here. And then we can compare that to the midday GCAS inequalities that we observe. And what we see that to within uncertainties, we actually see pretty good agreement between GCAS and TROPOMI in terms of the inequalities. So we're going to ask that same question in a different way. And in this case, I've plotted the TROPOMI data over Houston in the space of household income and the census tract fraction of non-white and/or Hispanics. And the NO2 data are low NO2 is in blue, moderate NO2 is in yellow, and high NO2 is in red. And you can see that the highest NO2 values are concentrated in census tracts where we have the lowest household income and the highest census tract fraction of non-whites and Hispanics. And then the opposite is true for the lowest NO2 values. So we can compare that here below. This is TROPOMI just along the GCAS flight path. We see a similar pattern. And then we can compare to the GCAS flight composite where we have a lot more variability. But again, we see this same distribution in this income, race, ethnicity space. So in conclusion, GCAS and TROPOMI capture similar NO2 patterns in demographic space. But we also see some issues that we need to be aware of here is that TROPOMI is capturing comparable relative, but not absolute differences. So you can see that reflected in the scale on the color bar. Here we're going from 1 to 5 times 10 to the 15, and here we're going from 1 to 30. And that also we see a shift in the distribution of NO2 from this log normal in the case of GCAS to normal in the case of TROPOMI. And we can explain this, one, we would predict it based on known uncertainties in the TROPOMI observations, which tend to miss the highest NO2 values, and also the fact that we're looking at an annual average of TROPOMI. Okay, so the next key element of using satellite data to investigate inequality is not in our case to know what the surface concentration is, but to know whether satellite columns are capturing the same pattern of NO2 as would be detected at the surface. So in this case, we'll look at this in 2 ways. The first way is through a comparison of surface monitor concentrations and satellite columns. And we do that as a function of distance to the nearest monitor. So here you're looking at a map of NO2 monitors throughout the city of Houston. And the coloration here is what the concentration is at that monitor. And then we do the correlation as a function here of distance from the monitor between the overhead column and the monitor itself. So we actually see really strong correlation coefficients between the monitor concentration and the directly overhead column, but we see that the correlation decreases as we move further and further away from the monitor. And it turns out we see a pretty steep drop in the correlation coefficient between 1 and 2 kilometers. And that correlation coefficient decrease actually corresponds to the spatial scales that we expect to see NO2 distance decay gradients at. So this is one piece of evidence that suggests that these columns are representing the same spatial patterns they're representing the same spatial patterns as measured at the surface. It also suggests, though, that the surface monitoring network is far too sparse to be representative for most people in Houston. The next thing that we do, and this slide's a little bit messy here, but as part of the Discover AQ mission, another aircraft measured the NO2 vertical distribution through the atmosphere 144 times. And you're looking here at a sample of 3 of those data, where altitude is on the Y and NO2 mixing ratio is on the X. And they collected these data in the morning, midday, and afternoon throughout the city of Houston. So we have information on the spatial distribution of the vertical distribution of NO2. And we did a series of correlations to test how consistently that NO2 was distributed vertically. And what we found was that there were no large location-dependent differences in the NO2 distribution throughout the column. And so this is the second piece of evidence that we have that indeed the satellite observations or the remote sensing observations were capturing the same patterns in NO2 as would be detected at the surface. So the last thing that I want to show in this section is that the satellite data are exciting because they also capture temporal patterns that are useful for us to interpret the causes of inequality. Okay, so this is actually the TROPOMI data just on weekdays. Then we have weekdays averaged to the census tracts. And now I'm showing you the NO2 distribution throughout Houston on weekends. And in US cities, these weekday differences are driven largely by changes in diesel trucking. So diesel trucks are largely parked on weekends, and we see this huge decrease in NO2 despite the fact that diesel trucks only constitute a few percentage of the vehicle fleet at any time in a US city. So this gives us a kind of an observational constraint on the impacts of diesel trucking. And what we see from TROPOMI is that inequality decreases by 25% weekend to weekday. And because we're still trying to understand what these observations, sort of like how far we can use these observations, we compared it to an inventory. This is a pretty specialized inventory. It has a spatial resolution of 500 meters by 500 meters. And predicted by this inventory, we would see diesel trucking would contribute 22% of inequality. So within uncertainties, we get the same answer as from TROPOMI, but we have this sort of direct observational constraint. The last thing I wanted to return to was this correlation of between NO2 inequality and regional air pollution, regional ozone air pollution. And what you can see, I've taken the last 2 years, or the first 2 years of the TROPOMI data set, so I've removed any influence on air pollution from COVID-19 shutdowns. And I'm plotting the NO2 columns on high ozone days. So these are defined as when ozone is in exceedance of the US EPA standard. And we're looking just at weekdays. And then we take all other weekdays, so any day in which ozone does not exceed the US EPA standard. And it turns out in 2018 and 19, this was about 43 days the ozone within Houston exceeded the US EPA standard. And then we repeat the NO2 inequality calculation, and we do indeed find that it's generally true that on high ozone days, we have worse inequality. So you're looking here at the percent inequality for people who are below poverty or near poverty compared to those above, and as a function of race ethnicity. And then again for LAN to HIW, which is this combined income and race ethnicity metric. So we find in this case that on high ozone days, NO2 inequality was 35%, but on all other weekdays, it was 29%. You really still see, though, despite this substantial decrease in NO2 visible in the image, these inequalities are persisting. So in summary here, we find that TROPOMI captures similar relative, although not absolute, demographic-based differences, that TROPOMI uncertainties work to bias inequality estimates low, and we could talk about this after the talk. The column variability within tract demographics reflects surface level variability. This was a really critical point for this work. And TROPOMI is poised to inform many aspects of the severity and causes of NO2 inequality within cities. So we'll now take this work and expand it to 52 cities across the United States. And we define these cities as census designated urban areas. So we're really looking here just at the urban core. And we use 2 years of TROPOMI observations. And we actually sort of mathematically average these to a resolution of 1 kilometer by 1 kilometer and average them then to the census tracts. We do this based on population weighted NO2 columns. It's the exact same method as I've shown throughout this talk. And now we compute inequality seasonally and by weekday and weekend. And I'm just showing you sort of a handful of cities below, just to get a sense for what these data look like. So here are the results from this sort of US-wide study. In this figure, you can see that the coloration comes from the NO2 inequality, which ranges from 0 to higher than 40%. And the size of the circle reflects the population of that city, with the most populated cities having the largest marker and the smallest cities having the smallest marker. And I'm showing you here on the right the averages from these 52 cities across the United States. And you can see that they're ranging anywhere between 6 and 22% based on which metric we select. But I also want to show here that there's a lot of variability in city to city, and the highest inequalities are 2 to 3 times these means, with the highest inequality that we observe as high as 67%. So now that we can look at these cities statistically, we're going to do 2 things. We're going to look at how the NO2 inequality varies with the overall pollution level. And I'm sorry, this should actually say weekday NO2 inequality. My apologies on that. And so what we've done is plot NO2 inequality on the Y and the total NO2 abundance in that city on the X. And so we can roughly see a correlation in NO2 inequality and total NO2 for that city. And we've separated the data here into seasons. So the gray circles represent the summer and the blue circles represent the winter. So we can see that absolute inequality is better correlated with and more sensitive to the city average NO2 in the summer when the NO2 lifetime is shorter. But, and so you can see that in these correlation coefficients in the lower right of the figure here. But what we do see also, which is not shown, is that the relative inequalities are not well correlated at all with city average NO2, suggesting that relative inequalities will persist even with NOx reductions. The other thing that we can do is conduct this weekend experiment for cities across the United States. And on the x-axis here, I'm showing you the weekday NO2 inequality for our 52 cities, combined to the weekend NO2 inequality. And the slope here, from the slope, we can derive the portion of inequality that's caused by diesel trucking, assuming that the full change is due to either direct or indirect differences caused by this change in diesel trucking. So again, we see that in the summertime, when it's gray, this correlation is quite tight. This is because the NO2 lifetime is shorter in the summer than in the winter. But generally, we see a pretty consistent pattern where diesel NOx emissions contribute approximately 35% of these NO2 inequalities. And so one of the key things about this diesel NOx emission is diesel doesn't just emit NOx, it emits a whole host of other toxic species. So really this is one of the main ways that NO2 has found its way to being used as a surrogate for toxic emissions in health studies. So these diesel trucks are sort of more harmful than just their NO2 emissions. So the last thing I'm going to show you here is we're still trying to understand the extent to which we can use TROPOMI to resolve these intra-urban differences. And so this is sort of an aspect of continuing that analytical analysis about the ability of TROPOMI to resolve those differences. So most US cities have some degree of segregation, and we can correlate inequality with segregation, and we find that NO2 inequality is statistically significantly correlated with segregation. And this makes sense that when cities are more segregated, we see larger inequality. But not all segregation is the same. In fact, we have structures of segregation that can be quite different. And I'm showing you a cartoon on the left here of how that segregation can manifest in a city, where it can be, in these two cases, we have the same extent of segregation, but the structure is quite different. So in cities like this, we have what we would call clustering. A city that would typify this type of segregation would be Atlanta. And up here, we have a high degree of evenness. A city that would typify this would be something like New York City, for example. So here we have, in both cases, the same amount of segregation, but the structure is quite different. And so if TROPOMI is struggling to resolve these inequalities within cities, it should do better when segregation is characterized by clustering than when it's characterized by evenness, because this should be something that it's better able to resolve. And what we end up seeing is actually there's no statistically significant correlation between inequality and structure. And so this is consistent with the fact that we see really steep NO2 gradients in cities, but also does suggest that TROPOMI really has sufficient spatial resolution to sort of address inequality even in cities where segregation is characterized by evenness. So to summarize this third part here, inequality estimates vary by season, day of week, and segregation extent, with a wide range in disparities across cities. And we see in the case of low-income non-whites versus high-income whites that inequalities ranged anywhere between 5 and 67%. Absolute NO2 inequality corresponds to citywide NO2 pollution when the NO2 lifetime is short. That diesel NOx emissions contribute approximately 35% of NO2 inequalities in US urban areas on average. So a few general summary points here is that certainly these high resolution airborne remote sensing observations offer really unique insight into air pollution disparities within cities. But also I think that these next generation satellites, this includes TROPOMI, which we discussed today, but this forthcoming satellite called TEMPO have the potential to not only advance our understanding of the causes and consequences of air pollution inequality, but also to be a really powerful tool for people to demand more from their policymakers. And just to sort of give you a sense for where we're headed with this work, we're interested in addressing the following 4 questions. The first is, because my background is in atmospheric chemistry, we're interested in wondering to what extent does atmospheric chemistry influence these census-tract level inequality estimates? How can NO2 vertical columns be analyzed as surrogates for other co-emitted compounds with more harmful health impacts? This really goes to that point that NO2 is a surrogate, often used as a surrogate for other toxic emissions. The third here is that, is it broadly true that ozone air pollution episodes are linked to conditions that drive ozone precursor heterogeneity? Meaning, like, is it broadly true that ozone air pollution is linked to NO2 inequality? And if we could reduce NO2 inequality, would regional air quality improve? And this would say, if we target inequality as policymakers, do we see regional co-benefits across the city? And finally, I've used heavily averaged satellite observations, but we're interested in answering the question, to what extent can daily satellite observations capture NO2 inequality? Perhaps they can't capture it fully, but perhaps they can capture a really important piece of it that we can analyze. So with that, I'll just stop and thank you for your attention and take any questions.
All right, thank you so much, Sally.
Yeah.
For questions, folks can either type in the chat if they wish, or you're welcome to just unmute at this time and ask. Either way, and I'll be monitoring the chat if you choose that way. Oh, okay, so here's a couple of questions from Dylan Malloy. The first is, given that air quality health impacts are to a large extent driven by aerosols with a range of sizes and lifetimes, to what extent do you think spatial gradients in total air quality health impacts would be weaker versus stronger than those for NO2?
I think that's a really good question. I think in the case of NO2, we're looking at something that should have among the steepest gradients. So I think then, certainly it would depend on the type of aerosol, in terms of direct emissions of like ultrafine particles, I would imagine that those gradients would be just as steep. But in something like secondary aerosol, those gradients are going to be much more, it's going to be much more smeared across the city. I think one of the things about NO2 that makes it interesting is it really lets us see where the sources are and see patterns in those sources. So, this idea that NO2 can be used as a surrogate, I think that there's a lot of interesting work for us to do to think about how we can kind of understand general air pollution inequality using just this sort of single species as the subject of study. But I mean, I think it would really depend on which aerosol. I don't know if that answered the question.
And then his other question here was, how do you think these inequalities are alleviated or exacerbated by the fact that people spend most of their time indoors, especially now?
Yeah, so this will tell us about outdoor exposure. I mean, and in fact, it also doesn't quite get us to exposure because we don't know the surface concentration. We only really know the distribution of sources and the distribution of pollution. So getting to exposure is another step that we haven't tried to tackle yet. I still think from a policy perspective, just knowing the distribution is still really important. In terms of spending time indoors, I think that it depends. I think that I'm not an expert on indoor air quality, but depending on if you have air conditioning, for example, your house is going to be more sealed up than if you don't, and you open the windows and you sort of allow sort of the breeze to move through your house. I would imagine in that case that then you would have greater exposure to outdoor air pollutants. Certainly, there might be someone who sort of studies how people sort of climatize their homes based on income, and maybe there would be a clue there.
Great. So there's a couple other questions in the chat. This is from Stephen Merrill, is there any temporal data available to indicate possible effects suggesting gentrification?
So the time records that we have for the TROPOMI specifically only go back about 3 years at this point. So that in that case, we can't really answer questions about patterns over time. But you certainly have the resolution to zoom into a neighborhood and say, what's happening here?
And a question about policy. This is a similar question that I have. Is, have you had a chance to share these results with policymakers, and if so, how has it been received?
So I gave a similar presentation to the to the US EPA in last month. And so one of the interesting things that I learned is the EPA is anticipating directives at all levels to incorporate environmental justice thinking into all elements of decision making. And so one of the things about regulating air pollution is actually we tend to think about issues of urban air quality like ozone formation and particulate as separate from issues of environmental justice. And those two communities, there's a lot of space between who's doing that research. And so if, for example, the US EPA was going to do a study where they look at like how ozone would change in a city based on certain controls, or how PM would change in a city based on other controls, environmental justice isn't typically brought into that analysis. So I think that they're anticipating, though, now that because of the new EPA administrator, because of the Biden administration going on the record for really coming out strong in the favor of environmental equity, that this is going to become integrated into all levels of decision making. So particularly questions about how environmental justice is coupled to air pollution, to atmospheric chemistry and regional air pollution. I think there's going to be a lot of interest in asking those questions going forward.
We have another question in the chat. It says, can the same methodology be used for determining inequality related to wetland ecosystem services or accessibility to level of clean water?
So that's a really good question. I can't say for certain, but I believe actually that there are satellite observations of products that tell you those things. And as long as they have high resolutions and sort of go high spatial resolution, and you can sort of like understand what the observation means at such a high spatial resolution, I absolutely think that questions like that could be answered.
Awesome. Okay, I think that's all the questions in the chat. Sally, I was just going to ask maybe if you can talk a little bit about sort of the caveats of using a satellite like TROPOMI. You touched on a little bit, talking about how there's kind of this low bias in terms of the inequality, and I'm assuming maybe that's related to vertical sensitivity and things like that. And so probably, given our broad audience, that might be helpful to just talk a little bit about some of those aspects of the data.
Yeah, so it's been documented and it's sort of understood that TROPOMI has a low bias when the NO2 columns are very high or when the pollution is very high. And so what that ends up doing is causing inequality estimates to be underestimated. And we tried to be as thorough as possible when we looked at whether we could use these data to do this work. And in terms of saying, sort of looking at each aspect of the measurement and saying like, what are the impacts of this bias, or what are the impacts of this decision, or what are the impacts of that? And what we found generally in each case was that we should be biasing the inequality estimates low. So in fact, they should be greater. The disparity should be greater. The gradient should be steeper. So I actually think, though, from a policy perspective, that's working in our favor. So if we came up with an observation where we were biasing the inequality estimates high, I think if we were going to go to a policymaker and use this as evidence for sort of where control should be focused and where different other decisions should be made, there would always be this question, I think, about like, well, have we overestimated, or are we being a little bit too dramatic in our assessment? So the fact that we have a low bias here, I actually think works in our favor, because we know that it's sort of at least this much. It's probably more. And so that I think that's a good thing in terms of convincing people to care. I do think, I still think that there's more to be done. I think that a lot of this really is sort of just committing to like going through each aspect of the observation and trying to be really careful about like what it can and cannot do. And I think that there's interest more broadly in this type of work to sort of use satellites to look at intra-urban variability, and applying it to inequality is sort of still doing that same kind of work, but in this specific application.
I had one other question, if that's okay, if there's time. Sally, that was a fantastic talk. So it looked like from your slides, if I read it correctly, you didn't see any cities with a reverse gradient. Is that right?
So we saw a handful of cities under certain seasonal conditions that did have inequalities that might have been, I'll use a minus sign for a reverse gradient, that might have been like -5 or, in some cases. Particularly in the winter time, you can see things start to sort of get kind of spread out in that way. But I think it will be interesting to look more detailed, sort of like, why do you have cities that have really low inequalities and cities that have really high inequalities? And what we're doing now is we're expanding that inventory analysis to go in all cities across the United States. So maybe we'll learn something about the relation, sort of what we would predict from the inventory versus what we see from the satellite. Is there maybe something about being a coastal city and you have the strong land sea breeze and you sort of redistribute that NO2 pollution? I think this comparison with the inventory will help us answer that. The problem though with the inventory is it's coarse if you go across the United States. We only have that at 4 kilometers by 4 kilometers.
You kind of hinted at what my next question was going to be, which is there anything about Houston is sort of a unique in terms of its meteorology that would make it more or less applicable to other US cities, do you think?
Yeah, so I think if you have a city that's right up against the ocean, I think you will see pretty strong impacts. So anytime that column, we did a lot of work to think about whether the satellite was seeing the same spatial pattern as would be measured at the surface. If those sort of profiles, those boundary layers were really shallow at the coast and then much higher as you move inland, I could see some of the conclusions that we drew about Houston, even though it's near the oceans, it's actually kind of set back a little bit. I could see maybe some issues in the relationship between the spatial patterns in the columns versus the spatial patterns on the surface. Absolutely. So I think Houston worked out to be a pretty ideal location to do this. It's geographically very large. So we have a lot of sort of the 1 kilometer by 1 kilometer really subsampled it really well. It's very diverse. We have large region of sources versus areas with no sources. So it turned out to be a pretty idealized place.
I see there's a question in the chat about articles for your methodology. I think you mentioned one at the beginning. So I would invite this person, I think in the recording you have some information about that at the very beginning there.
Yeah, we have a paper on the methodology that came out this summer in 2020 in Environmental Science and Technology.
Perfect. Okay. Are there any final questions?
Well, I just wanted to thank you all again for giving me the opportunity to speak, and yeah,
thank you so much for being here, Sally. I agree that was a wonderful talk, and we appreciate you being here in this virtual world that we're in. So thank you again, and thank you all for being here.
All right. Bye, everyone. Bye, Dylan.
See you later. Nice to see you.
Nice to see you too.